Hello everyone and welcome to this presentation which is all about solving inequalities. We're going to look at linear inequalities, quadratic inequalities, and we're also going to be graphing inequalities as well. To get the ball rolling, I'd like to have a go at these 5 inequalities please. They are all linear. I'd like you to isolate x and I'd like you to be careful. Please remember that rule that you learnt at school, that if you ever have to divide or multiply by a negative number, the inequality sign will change. If you are clever enough with your manipulation though, you might not need to use that rule, but that's completely up to you. So a couple of minutes, have a go, press pause, and then when you're ready to get some answers, I will go through them. Okay, good. So part A then, we would take x off both sides and we would add 3 to both sides and we would end up with x is less than or equal to 8. On B, we would take away 6x from both sides, would be fine, and we'd end up with minus 3x is less than 4. But then if you divide through by that minus 3, don't forget to swap the inequality sign because you're dividing by a negative number and you will end up with x is greater than minus 4/3. The alternative for B, of course, is if you take 3x off both sides first and then take away 4 off both sides second, you won't have to worry about that change in inequality sign because you've kept the x's positive, but that's your choice. C, the first thing you would do is multiply everything by 8 and you would end up with 56 minus 24x is greater than or equal to x plus 7. And then if you perform the same sort of rearranging as we did in A and B, you should end up with x is less than or equal to 49 over 25. Please don't worry about the fact that it looks a bit of an awkward fraction. That's perfectly acceptable, of course, doesn't simplify. In D, you've got choices. You can multiply out the brackets first, you can divide by 3 first, it's completely up to you. But again, using those skills that we've seen in the previous 3, we would end up with x is less than or equal to minus 1/3. And then finally in E, you are going to have to multiply by minus 3 to begin with, or that seems like the best option to me to start with. But when you multiply by that minus 3, don't forget to swap the inequality sign. And then you would add 6, you would divide by 5, and you will end up with x is greater than minus 3. So hopefully they are okay. If they're not, please contact your teacher and they will be able to help you with the solving of those 5. Okay, good stuff. So the next slide is for your notebooks, please. And what we're going to do is we're going to plot each of these 2 lines and then we're going to do something with them. So you might want to wait just a minute until you see how this develops before you draw anything in your notebooks. But here are my axes. This is the line y equals x plus 5. It has a y-intercept of 5. It has a gradient of 1, etc. It would have an x-intercept of minus 5 had we drawn the scales differently. For B, which is our y equals 2x minus 3, we have a gradient of 2. There is an x-intercept of 3 over 2 and a y-intercept. If we had have seen more of the y-axis, the y-intercept would be minus 3. And if I wanted to find where these 2 lines meet, in other words, solving the simultaneous equations that you see at the top, then we would be putting those 2 equations together using that substitution method that you learnt in the simultaneous equations presentation. And the solution to this particular equation would be where those 2 lines intersect. And we learn that at school, that the solving of 2 linear simultaneous equations gives us the point of intersection between the 2 lines. And the answer is x equals 8. And you could of course find the y value by placing it into either of the 2 equations. But you can use this graphical method, the idea of drawing the graphs and looking at the graphs to find something out about them. you can use this method to solve inequalities as well. So here is a question. It's a similar question to the one we've just seen on the first slide, but we are looking at where x plus 5 is greater than or equal to 2x minus 3. Now, if we are looking at this graphically, the way that we would talk about this inequality is when is the graph of x plus 5 above or equal to the graph of 2x minus 3. So I'm now going over to my graph and I'm looking to see whereabouts is the light blue graph higher up than the purple graph. And these red lines or red arrows are showing you exactly where that is. So all up until the point of the intersection, the graph of x plus 5 is higher up or above the graph of 2x minus 3. And you can see that the red line along the bottom x-axis now is indicating where the values of x are that we want, the ones that are working, the ones that are important to us. So any value of x, as long as it is less than or equal to 8, will give us an answer that works for this inequality. So the solution to this problem is that x is less than or equal to 8. And we could find that answer, of course, by solving the inequality in the same way as we did on the first slide. But this method works for when we've got equations and inequalities that are perhaps harder to solve algebraically than these. So the graphing method is a great way of solving just by using the graphs rather than using the algebra. Okay, so a good example of that is shown here. Quite a tricky little inequality to solve algebraically. So what we will do is we will have a go at solving it graphically instead. So we're going to draw the graphs of y equals x squared plus 3x plus 5. We'll then draw the graph of y equals 5x plus 8. And then we'll have a look at those two graphs to find where the quadratic is less than 5x plus 8. So again, the idea is that we plot both of those curves and then make decisions about where the x values are that work. So this is the quadratic. You can plot that by using the skills that we've done previously on quadratic. So there is a y-intercept of 5. You could complete the square to find where the minimum point is. There are no x-intercepts, and you could use various methods to determine that. So there is the quadratic. And here is the straight line. So y equals 5x plus 8 has a y-intercept of 8, has a gradient of 5, and has a x-intercept of minus 8 over 5. And what we want is the points of intersection first. So whereabouts does the quadratic and the line meet? And there are 2 points, you can see them, and the first one is where x is minus 1, and the second is where x is 3. So it's always important to find where the intersection points are first before you start looking at the actual inequality. So minus 1 and 3. What we now need to do, and this is the inequality section, is say when is the graph of x squared plus 3x plus 5, when is that graph below the graph of 5x plus 8? And the reason why we want to look at where it is below is because of the less than sign in the inequality. So where is the quadratic less than 5x plus 8? Where is the graph of the quadratic below the graph of the straight line? And again, these arrows are indicating where that is. And it just so happens that it's all the points of x between the two intersection points. But it's not including the points of intersection because of the strictly less than inequality. So if it's less than, it doesn't include the minus 1 and 3. If it had been less than or equal to, then it would have included the minus 1 and the 3. So the solution is in between those two values of x, but not including them. And the way that we would write that is as a single inequality, and you can see it written there at the bottom of the screen. Okay, so is that the only way of solving that problem? The answer to that is no. So we can also solve this inequality by rearranging first into something that looks a little bit more friendly and then dealing with the graph that we end up with. So let's have a look at that in action. So I'm going to rearrange this inequality by making everything over to one side with 0 on the right. And I'm keeping my x squareds positive. So I've brought the 5x over to the left-hand side, I've brought the 8 over to the left-hand side, and that ends up with an inequality x squared minus 2x minus 3 is less than 0. Now that's no different to the inequality at the top of the page, but it's just a little bit more user-friendly. But the way that I'm now going to solve this inequality is exactly the same as I did on the previous slide. So I need to find, first of all, some points of intersection with the x-axis, the 0. So I'm going to do that by factorising, and that gives me x values of -1 and 3, or 3 and -1, depending on how you look at the two brackets. So here they are, 3 and -1. Now, clearly they're not the answers to the inequality, they would be the answers to the equation. But they do give us a good starting point by finding where the two brackets are equal to 0. But now we need to look a little bit more in depth at how we work out where it is less than 0. So to do that, we're going to sketch the curve. But we only have to draw one curve this time because there is only one curve on the left-hand side. The right-hand side is now 0. So the curve itself looks like this. This is the graph of y equals x squared minus 2x minus 3. You can see that those roots of -1 and 3 that we've just worked out are clearly shown on the graph. If we needed to, we would be able to say that the y-intercept is -3, but that's not important. We would also be able to work out the turning point, but again, that's not important. The only thing I'm interested in now is going back to the inequality, x squared minus 2x minus 3, and looking to see whether it's less than 0 or greater than 0. Now my quadratic is, where is this quadratic less than 0? Where is it below the x-axis? And I can see that all the points of x between -1 and 3 will give me a value that is less than 0, below the x-axis. So again, the solution to this question would be all values of x between -1 and 3, but doesn't include -1 and 3 for the same reasons as we said on the previous slide. So there is my final answer. Not coincidentally, of course, the same as the previous slide. Okay, good. So continuing in our notebooks, we're now going to look at a different way of writing our answers other than inequalities, and that method is called set notation. So I shall give you 3 examples here of the 3 different types that you might see. So this is set notation, and we just have to describe what each of these different symbols are and how set notation works, and then you can use set notation for other such questions in the future. So first of all, curly brackets, always used for set notation. We then need a variable, and 99% of the time that variable is going to be x, but of course it could be any letter. But x for this example, or these examples, because it's the x values that we are looking to find, and then the conditions of that variable. So in this question we need to make sure that x is less than or equal to 3. But what about the inequality that we had on our previous slide? Well, here is an example that looks very similar to that. We want x to be between 2 and 4, but not inclusive of those values. So how would we write that using set notation? Well, it's important that we understand that what we want here is x is greater than 2 and we want x to be less than 4. So here is the set notation for that. We have to write it as 2 separate parts, and then this symbol in the middle of the 2 parts is the and symbol in set notation, but we'll look at that in due course. So and symbol, and the fact that x has to be less than 4 and x is greater than or equal to 2. But there are times, for example, in that previous slide, what would have happened if we were looking at where the quadratic was greater than 0? That would have been occurring in two different places on the graph. So there are times when our inequality doesn't look like the second example, where x is between two values. Instead, we have x in two different places completely. So this last example is when x is less than 5, or in another place where x is greater than 7, two completely separate parts on the graph. So in this example, we have to use the symbol for or instead of and the symbol for that is this one here. So again, we've got our x needs to be less than 5, we've got our x needs to be greater than 7, but it's one or the other. So we use this symbol in set theory to represent or, and you will also see these symbols come up when we do probability in the statistics section. Okay, good. So as ever, it's time now for you to test your skills on what we've looked at so far. So on page 31, exercise 1.2, have a go at those questions, take your time, get some good practice on that skill. Any problems, ask your class teacher, please, and then when you've marked them and you've understood what's going on, we will move on. Good. So again, in your notebooks, what we're going to do in this final section is to look at showing the region that satisfies a particular inequality. So we're going to be showing this inequality on an XY plane. And the way that we do that is to first of all plot the graph of y equals 2x plus 5, and then we'll worry about where the y is less than or equal to 2x plus 5 once we've done that. So y equals 2x plus 5, of course, is a straight line. Gradient of 2, y-intercept of 5, passes through the x-axis at minus 2.5 or minus 5 over 2. So these are all skills that we learned in the straight line section. And now what we need to do is not to concentrate on the y equals, but whereabouts is the y is less than or equal to. And the way that we're going to do that is to concentrate on a single point either side of the line. It really doesn't matter where you choose your point. So I'm going to choose the point minus 1, 1. That's completely arbitrary. I could have quite easily chosen the origin if I wanted to, but I've chosen minus 1, 1. And of course, for this particular coordinate, the x value is minus 1 and the y value is 1. So what I'm going to do is I'm going to place those values into the inequality. And if it works, if that then forms a true statement, it means that minus 1, 1 is on the side of the line that I do want. And if it doesn't work and I find that I end up with a false statement, then the coordinate that I chose is not on the side of the line that I want. So if I do a bit of maths on here, 1 ends up being less than or equal to 3, which of course is true. So that's good. That means that our point that I've chosen at random is on the right side of the line for my inequality. So what we do is we shade the part of the graph that is false. So the part that remains unshaded is the bit that I am actually interested in. Sometimes you can label that region that you are interested in. Sometimes it's called the feasible region. So that would be a nice way of showing the area that you do want. But if you are going to use shading, then you shade the side of the line that you don't want. So if your point is true, which is exactly what we've got here, shade the opposite side. And if your point is false, shade that side where your point is. Great, so here's a slightly more complex question than the previous slide. What we've got here are two inequalities. One of them is a linear inequality, one of them is a quadratic inequality, And what we're going to do is look at showing the region on the graph that satisfies both. So we shall start by looking at just one of these. So let us start with our y is less than or equal to 2 minus 3x. And we are going to first of all look at drawing the line of y equals 2 minus 3x. And this line would be a straight line with a gradient of minus 3. It has a y-intercept of 2 and it has an x-intercept of 2/3. And again, you know all those skills from the straight line work that we did in a previous presentation. However, you will notice that the line this time is a dotted line. And the reason why we've drawn it as a dotted line is because the inequality is a less than inequality. It does not include equals 2 minus 3x. So that the way that we indicate that we're not interested in the point actually on the line itself is to do a dotted line. On the previous question, if you go back to the previous question, you will notice that it was a less than or equal to, or a greater than or equal to, and therefore that is the reason why we drew a solid line, because it did include the points on the line itself. But in this case, we're not interested in those points, so we only use a dashed line. Now again, forget the quadratic for now. What I'm going to do first is just look at the region for the straight line. So I'm going to choose a random point, and this random point that I've chosen is 2, 4. Again, completely at random, that point. And I'm going to place those values into the inequality. So I end up with 4 is less than 2 minus 3 lots of 2. A quick little bit of numeracy, and it works out that 4 is less than minus 4. Now clearly that is not a correct statement, that is false. So what that means is that the point that I've chosen is not on the right side of the line. I don't want that point. Okay, I want points that are on the other side of the dotted line. So because of that, from the work that we did on the previous slide, I'm going to shade in that false side. And so all the points that I do want now are shown in the white section on the graph. We're now going to do exactly the same, but this time we're going to look at the inequality y is greater than or equal to x squared minus 3x minus 4. Okay, good. So let's have a look at this quadratic. So the first thing I want to do, again, like with the linear, is I want to plot y equals x squared minus 3x minus 4. And I can do that using all of those skills from the quadratic section, but I can factorize it and work out that the x-intercepts are at minus 1 and 4. I know that the y-intercept for this curve is at minus 4. I could also use completing the square methods to find where the minimum point is as well. So I can find lots of really detailed information about that quadratic, and then I can sketch that quadratic like you are seeing on the right hand side. But I need to find where y is greater than or equal to x squared minus 3x minus 4. So once again, I'm going to choose a random point. So the point that I'm going to choose is the origin, so at 0, 0, just to illustrate that that's a perfectly acceptable point to choose. And if I put x is 0 and y is 0 into my inequality, I can work through the maths and find that 0 is greater than or equal to minus 4, which is true. So the origin is in the part of the quadratic graph that I need. So I'm going to have to shade in the bit that I don't want, which is all of this section here. It doesn't matter if you double shade, you know, you've already shaded some of this for the straight line, it's fine, or you can just shade in the bit that that leaves you with the bit that you actually want. But you can quite clearly see now from doing the maths that the white part of this graph is the section that I need. So this would be my solution, as that is the bit that remains unshaded. Great stuff. So again, over to you. There are some questions in this exercise that look at sketching inequalities on an XY plane based upon those skills that we've just mentioned, either linear or quadratic, or as in the last example, both. So yeah, by all means, please practice this skill, have a go. Any problems, speak to your class teacher, and we'll take it from there.